Today we would be learning about longitudinal data. Previously we have learnt about regression and regression techniques. So, in longitudinal data we would extend the idea of this regression under a correlated setting. So, what we would learn is what is longitudinal data, what are the defining features of longitudinal data, why do we use longitudinal data, and what are the advantages of longitudinal data. In the process, we shall see a couple of examples of longitudinal data set, and we would just introduce ourselves to the methods that are used to analyze our longitudinal data. There would be a specific video on how to analyze and visualize longitudinal data later on in this series, but in this introductory class we would see how we can effectively use R to get a glimpse about the longitudinal data. Finally, we shall see what are the notations that we use for longitudinal data and all the statistical modeling techniques that can be used in context to longitudinal data. So, the objective of this introductory lecture in longitudinal data is to state what is longitudinal data and the features associated with longitudinal data, its advantages and its disadvantages. Then we shall see examples of longitudinal data, we shall see the notations of longitudinal data, and finally the models that are used for longitudinal data.
Now, longitudinal data means repeated measurements on each unit. Here unit can be an individual, a unit can be a person, unit can be an animal, unit can in general be a subject on which the measurement is made, and this measurement is made repeatedly over the subject. Now, how is it different from cross-sectional data? Typically, a cross-sectional data has a single measurement on each unit. And there is another type of cross-sectional data called the repeated cross-sectional data. Here, repeated measurements are made, but the repeated measurements are made not on the same unit, but on different units. So, epidemiological data are generally data or single survey data which are generally cross-sectional and data. Now, longitudinal data are sometimes called panel data in context to econometrics or in economic statistics, and cohort study in context to epidemiology. Now, what are the advantages of longitudinal data? The first advantage is that we can model the mean response with time and covariates. But there is another advantage. Longitudinal data allows us to model the variability, and variability creeps in by the very nature of the longitudinal design. Here, because we take multiple measurements on repeated individuals, there is a heterogeneity between the individuals, and these are typically called the random effects, and we can model it using a random effect strategy which would come much later in this course. But also there is something called a serial correlation. Now, what happens is, if measurements are taken over time, then two measurements which are closer in time would be more similar than measurements which are distant apart in time. Now, to incorporate this idea, the idea of serial correlation comes in. Finally, as with any statistical model, there is a measurement error. Now, longitudinal data allows us to model all the three variability components independently. Now, why do we need special methods? Why not ordinary least squares? Because ordinary least squares has a huge applicability. The problem is that ordinary least square assumes something called a spherical error variance, which translates to that there is no heteroscedasticity in the data and there is no serial correlation in the data. However, the repeated observations are likely to be correlated, and by the very design of longitudinal studies, there is heteroscedasticity and there is serial correlation. But still, if we ignore the correlation and use least square instead, the first thing is that sometimes in scientific inquiry, the correlation may be of importance. Secondly, if we use the OLS estimates, then it would give unbiased estimates, but they would be inefficient in the sense that the precision of the estimates would be lost. It won't be exactly precise. And finally, this would lead to incorrect standard errors. And so the inferences based on standard errors would then be incorrect. So as an example, let's say the famous data by Pathoff and Roy called the orthodontic data. Now this data had study on 27 children, 16 boys and 11 girls. And for each of them, the distance from the center of the pituitary to the pterygomaxillary fissure is measured. And this measurement is taken 4 times for at the ages of 8 years, 10 years, 12 years and 14 years. The R package NLME has this data stores inbuilt, and that is called the orthodont data. So we can install the package or the library NLME, and we can call the library NLME in R, and if we write head orthodont, then what we would get is we would get the first few entries of the dataset. So as you can see here, we have the distance, the age, the subject and the sex. So the subject is indicated by M-01, M-01, M-02, M-02. So that means male 01 and male 02. Similarly, we have F-01 and F-02. So we have 16 males and 11 females. Now, what was the goal of the analysis? The goal was twofold. First was to determine whether distance over time are larger for boys or than girls, and then to see whether the rate of change of distance over time is similar for boys and girls. So the first thing that can be done is to plot the orthodont data, and orthodont data is an object in LME. Since it's an object in LME, I can have a plot command of it, and the moment I plot it, it gives me a nice plot with each panel indicating each child. So here is the panel name of the child's M16, M05, so M16 stands for male 16 and so on and so forth, and here are the 4 measurements joined by consecutive lines. Now, to start off with, if we had only one child with 4 measurements, we could have done a simple OLS regression on that child, and then we can extend this idea and do the simple regression analysis on the 27 childs. The LMList function in LME exactly does this, and when we plot this, what do we see? We get an intercept and a coefficient of the age for each of the 27 childs. And when we plot this along with their confidence interval, what do we see? We see that both in terms of intercept and in terms of age, there is a variation. So it is that the intercepts and the age are not in a straight line, but they are scattered like, so some are on the right side and some are on the left side, meaning that there is individual level variation. Now, this is the unique feature of longitudinal data, that it allows us to explore this individual variation. So what do we see from the overall orthodont data? We see that the trajectory is approximately linear is a linear function of age. Fine, but there are exceptions. The trajectory vary between childs, indicating the presence of individual level variability. The distance measurement in general increases with age, but again there are variations. And the distance trajectory for boys are higher on average than for girls. But Also in this case, there are exceptions. So what do we see? We can conclude that there is a population level trend, there is a mean trend, but there are subject specific variations in the data. The next data is the multicentric AIDS cohort study. And here 369 AIDS infected individuals are taken, and over time their CD4 plus cell number is noted. Now CD4 plus cell number, or CD4 plus cell counts as we say, is a measure of a person's immunity, and what AIDS virus does is it depletes the CD4 plus cell counts. So what has happened is 369 individuals are followed over time, and they are followed pre-seroconversion. Seroconversion means from the time, from the instance when the AIDS virus has started to show its symptom, and they are followed over time. So here what we see is that here there is 2376 observations. So the total number of observations is large, and in general no trend can be seen apparently from the scatter plot. So we have added a smoother on it, and we shall see about the details of the smoother in the next lecture. But here the smoother indicates that with time definitely the CD4 cell numbers are depleting. So the scientific question of interest here is, what is the impact of HIV infection over CD4 plus counts? Finally, we have the seizure data. Now the seizure data are the number of seizure counts for 59 epileptic patients who are randomly given a drug called Progabide or a placebo. And this data is also available in the R package mass as APIL. So to see the data, we can call the library mass, so library mass, and then head APIL, that gives the first 5 or 6 rows of the data. Now we can have a box plot of it, and this is what we have done here. So the box plot is a conditional box plot. So condition on the treatment, the placebo or Progabide, we have seen how the log count of seizures is varying as a factor of time. So here the question of importance is whether Progabide is able to cure or decrease the number of epileptic seizures or not. Now the fundamental feature of all these 3 examples is that here we have repeated measurements on individuals. In the first 2, the measurement was continuous variable, while in the final one it was a count variable. So to generalize the idea, we say that we have M units, and generally it's denoted by I. So I denotes the unit of the subject, and I ranges from 1 to n. The number of observations is denoted by Ni. So it's J. So J ranges from 1 to Ni. That means for the ith unit, I have Ni observations. If N1 equal to N2 equal to Nm equal to say a constant number, then we call it a balanced design, else the design is called unbalanced. Typically, a response is denoted by Yij, where I indexes the unit and J indexes the time, and Tij is the time at which Yij is measured. So we have the vector yi1, yi2, yini denoted as capital Yi. The mean of each is denoted by mu ij, the variance of each by small wij. The expectation of the vector capital Yi is mu I, and the variance of the vector capital Yi is Vi. And covariance of Yij, Yik is variance of I, Jk. So that's the jkth element of the matrix Vi. Now there are 3 ways of modeling a longitudinal data. The first is the marginal model. So what happens in marginal model is that the focus of the model is to see what's the mean level, what's the mean trend. So we have basically two models. So one models the mean, and one is that the variance is modeled in terms of a few lesser number of parameters, more to come in the marginal model example. The second is the random effects model. In the random effects model, what happens is every individual is modeled, and then the parameters are very individual specific. So there the parameters are again modeled in a second level. So here, as you can see, Yij given beta I is Xij transpose beta I, and then beta I is modeled as beta plus Ui. Finally, we have the transition model, where it is thought that the yjth observation or the jth observation of the ith unit depends on the previous observations. So here, instead of modeling Yij conditional on Yij minus 1 to Yi1 is modeled.
So to conclude this introductory session on longitudinal data, let us recap what we have learned. Now, repeated measurement on individuals leads to longitudinal data. Longitudinal data is advantageous in the sense that it allows us to model the individual level heterogeneity present in the data by proper statistical techniques. We also learned how to use simple functions in R to visualize some basic longitudinal data. There were 3 data sets introduced in this session. We shall be repeatedly using these data sets for further analysis and to illustrate the different statistical procedures that can be applied on longitudinal data. In the next video, we shall be talking about how to analyze or how to visualize large scale longitudinal data.